Yes, Plinio, it's visible
Yes.
now. Yep.
Okay. Yeah, agora como é que eu tiro esta coisa? Só me está aparecendo assim, não percebo.
Isso é mesmo se não é no Zoom, isso é mesmo na apresentação.
Na apresentação.
Já está.
Okay, so now you should be able to see the screen in the full resolution. So, hi everyone. So my name is Plinio, and I'm going to give you like two seem to be different research approaches, but both of them are guided by vision. So I'm going to start first with the outline. So I'm going to talk basically about two things. One of them is object grasping, so how a robot can actually grasp an object using visual input. And there are two examples: the task-based grasping and the fragile object grasping. And then afterwards, I will talk about how to use vision for human-robot interaction. So how we can have some engaging behaviors through vision and tactile sensing. Those are the two big subjects. And then starting with object grasping and the task-based grasping. So what is vision-based object grasping? So we have a very large inspiration from human approaches. So when we are grasping an object, we use vision first to look at the environment. We realize where the object is, and then afterwards we move our hands to grasp the object using mostly vision until we start to touch the object, and then we use tactile. In this process, what we are trying to define is this reference frame that is here on the hand. So we are trying to decide where to put that reference frame. So what is the position and orientation of the hand that we should actually define to have a successful grasp. So to do that, we usually execute two steps. So the first one is extract those visual features using just the camera, and then what we see from in this case, the camera for the robot and our eyes, and we extract some shape information of the object that would be fundamental to have successful grasping, and that is the first step. And then I refer that here as a function of the image. So those are some numerical values that represent the shape of the object. And then afterwards, the second step is, according to those visual features, I want to build a map that actually generates a pose of the hand with respect to the object, and that pose should lead to a successful grasp. And that is the second part. And in the second part, I have this P that represents the probability. So it's the grasping probability of a certain pose of the hand. And that's what actually we want to compute. And we want to maximize that. We want to find which pose with respect to the object would maximize this grasping result. And on the right side, we have an example. So we have the field of view of the camera with those gray lines, and we have the pose of the end effector. In this case, is a humanoid-like hand that we want to place next to this object to have a successful grasp. And this is a very quick summary of vision-based object grasping. I'm going to show you two approaches. The first one is the task-based grasping, and then I'm going to talk about another one, the fragile object grasping. So in the task-based grasping, this was part of a European project that had a mobile robot, that had a two-finger gripper, and it was more in an industrial environment. And the second example is about a project that Jose talked about, Professor Jose, about archaeology, about the Pompeii frescoes. And in this case, in the second case, the end effector is a soft material hand that it was particularly chosen to avoid damaging the objects. And then on the task, starting from the task-based grasping. So this was a big collaboration between several partners, where we had as anybody can can actually know about this. You have some in ChatGPT, you can put a lot of inputs, and then according from the input, you can get some outputs. And in this case, that was a long time before these approaches exist, so we had to define the input from the user in a very particular keyword way. But there were the actions. So basically, in this case, the user says to the system, pick all the bottles in order to pick and place. In the case, pick and place on the bottle in the cupboard, pass a cup, pour out liquid. So this kind of input. And according to the input, we have to execute these motions, get to the right place, basically select the right part of the object, and then execute the grasp. In all these things, so what we decided was to create a model that takes into account different things. So, and in this pipeline, what we have first is each one of the objects that we have, we divide them in parts. So we have this case, you see the point cloud of a champagne glass, of a cup, of a hammer, of a pen, and then you have each part. So you have to basically find these parts, and these parts are important because these parts convey different tasks. So in this case, the pen, you have the handle, the hammer, you also have the handle, in the cup, you have the handle, and then for the handle, you can actually define a particular set of actions. In this case, use the object. We have the parts, then somehow you have to recognize which type of object are you going to grasp. In this case, it's a pen, a cup, a tool, glass, and then you have to do this, what I'm named task-based grasping, that you have to consider the part of the object, you have to consider the geometry of the object, and you have to consider the task that you are executing. So according to these three constraints, you define in which part is the best one to execute the grasp. So in this case, we have the part that we have is top, middle, and bottom, and the handle. And then afterwards, after having the parts and the geometry, then there is a part that generates the grasping hypothesis according to these constraints, according to the task that you are going to execute, the part of the object, and the geometry. So mostly what we did here at the Institute of System and Robotics was to generate the grasping hypothesis based on the shape. Yeah, so we have both high level and image-based grasping. So in the high level, what we have is this, what I just explained. So the object is divided into actionable parts. So each part has a particular set of actions that you can do. In this case, for example, the top part is to pass the object, the middle is to pick and place upside down, for instance, the bottom part is to store in a shelf, and the handle is for tasks such as pouring and pick and place. So according to this task, basically you define which is the part that you are going to grasp. Then we combine that information that is called high level with the low level one, that in the low level one is from the image that you get, the image that the robot has at some point. You have to compute some visual features that could be 2D or 3D that extract the shape of the object. And what we do during learning is basically place virtually the end effector at multiple poses. So you can see here the poses reflected by these three arrows here. We basically play virtually this end effector in these different poses, and for each one of these poses we have a grasping label. So the grasping label says if for this pose the object is graspable or not. And yeah, so what we do is compute this. So do this in multiple parts of the image to basically decide where I should put the end effector with respect to the object. And the output of this basically is the grasping probability for a certain set of image features. Okay, so this is a very quick summary of this, and I'm going to already show you some examples. So on the left side, you have You have here the experimental setup is a KUKA arm with a 3D range camera, and the idea is that this approach selects the right part. So in this case, is to pick and place this champagne glass. So it's selecting what is the pose, is selecting what is the pose of the gripper. And in this case, the selected part was the bottom, because the bottom is the best part to do this task. In this second task, the bottle is sideways, and we want to pass the bottle. So the best way to grasp it is to actually grasp it from the middle of the object. And then finally, this pick up on the table. So in this case, the best part to grasp the object is on top, and these are all the successful grasp. The same, and well, finally, this is the pot or the pan that we should grasp it from the handle for the task that is in use. Then I'm going to show you another video here that is the fetch and carry demo, and the same system was used for a different task. That in this case the task was to put all the bottles, so basically find all the bottles and place them in the case, and you will see the bottles and the shelves and the multiple parts that we use for this demonstration. So you have the mobile robot with the KUKA arm, the gripper, and the camera that is leading the grasping. So now, yes, now it's starting to move. So the robot navigates autonomously. So all this demo is totally autonomous. Then after navigating to the point, it grasps the bottle and places it in the case according to a predefined position. Then it navigates to the next shelf, and it's going to aim to grasp the bottle. And in this case, it doesn't succeed. So it's but goes again and again all over the shelves, executing the actions. This is the second bottle. And then in the last the last part, it goes to the table, and then on the table, due to the constraints of the limitations of not hitting the table, then it grasps the object grasps the bottle from the top part. Okay, so this was the first example I wanted to show you. Then the second part that I want to talk about is the same problem. So in this case, instead of objects in an industrial setting, where we want to grasp our these fresco fragments that you see on the top image, and we have a conservation constraint, so we are not allowed to touch the painted part, and we cannot exert a large force on the object, otherwise it's going to start to fall apart. And even the archaeologists, they have to be very careful with this, otherwise the fragments start to get smaller and smaller across time. So the solution of this project is we have a bimanual arm that you see on the bottom image, and the end effectors are designed with some materials to basically to avoid damaging the fragments. This brings a limitation that we don't have that many degrees of freedom to control the arm, so we are also using vision-based algorithms for this. In this video that is going to start soon, so I'm going to show you like a little demo of the vision-based grasping. And the key part in this demonstration is that since the camera has a point of view that cannot see entirely the object, So we have a learning algorithm that that is able to complete or basically generate the occluded part of the object. So if you put it in terms of generative algorithms, is basically to hallucinate about the not visible part of the object. So, and here you can see that the green point cloud is generated just seeing the red one. So after completing the object, then the our approach then plans for the pose. So select, as you can see in the red circle there, the pose of the hand with respect to the object. So the pose of the hand, and the hand is going to move to that pose after the motion planning is executed. So you see they are moving in simulation, and then it's going to move in the real life. It's going to approach the fragment, and then after reaching, then it's going to close and lift the object. So yeah, it was successful. So, and this is another example of vision-based grasping. So this was the second example, and so the message that I want to pass to everybody is that the vision-based approach for grasping is very human-inspired, and that is basically vision guides most of the time until tactile feedback finishes the task. You saw that the robot, they executed lower speeds, so that's a big limitation because it would take a long time to execute the tasks. And also tactile sensing currently is limited. So, and that's one of the limitations that actually we are also working on. So, and yeah, current approaches are using a lot large language models, and also what they do is try to join basically features that consider both the images and text descriptions of the images. And these are the take-home messages of this part. Then I'm going to move to the second part that is about human-robot interaction. And in this case, I'm going to start by defining what is that. So we have we humans also do this a lot. So we looked at the other persons, and we try to estimate where those persons are looking at. And also we try to detect which gestures they are actually doing, and according to that we decide what to do. So all these gestures and gaze directions and motions is called non-verbal communication. So on those non-verbal communication cues that we detect from vision actually lead us to execute the interaction actions. So from vision, what we can do, estimate the gaze direction, recognize the gestures, and predict the motion of other actors. And according to that, we decide what to do. And we also want our social robot to do that. So we want to, let's put it like from a play point of view, to replace one of the persons by the social robot. Then, so when we use one of the things that we implemented in our social robot is, well, how we manage to call the attention of the person that are around. So in this case, is simply detecting the faces from the image point of view, and then after detecting the faces, then we guide the gaze of the robot towards the face of the persons, and then the persons actually react to that. So, or they do two things. One thing is they try to engage in interaction, or they avoid, like that woman did right there in the video. So in this case, the visual input is the image that the robot is looking at, and then from the faces we guide the head of the robot towards that point, and with that we are able to engage into interaction. Then in this case, the robot is navigating, is actually trying to, as soon as it detects one of the faces, then points its camera towards that puts basically the face in the center of the image. Okay. Then, when we are trying to engage in interaction, in addition to gaze, so we want to use other nonverbal cues, such as arm gestures, hand gestures, and those ones convey additional information. So in this case, in the video, the robot looks into the direction of the gaze of the person, and then executes a waving motion to engage interaction. And after that, then the person also replies in a way that executes similar gesture, and the robot is also detecting that gesture. And we use this kind of perception to guide the robot to execute a greeting model. So a greeting model is a model that most of the Western persons use to greet, and then greet is the starting point of the interaction. Okay. And finally, so only the nonverbal is not enough. So actually, we have to actually get in touch with the physically with persons to have better interaction. In this case, what we see here is the same social robot going and engaging interaction with the president of the current president of Portugal. So, and then first actually is going to at some point execute a handshake, and then the handshake, well, actually includes that physical part, the touch, that is also important to engage into interaction with people. So okay, and I want to just to actually remind you about the main messages. So the first one is that we can detect nonverbal communication cues with cameras, and those cues are very important for engaging into interaction. I'll show you examples of how can this be done with the social robot, and then so vision leads the decision making. There is something very important here, the social factor. So every person has its own mind, and it's very difficult to have something that works for everyone. So it's challenging in that way. So it's you have large variability. So so the conclusions are limited to these control settings, and we would like to have it running in the wild, but that is not yet there. So yeah. So this is what I wanted to say. So thank you very much, and please ask questions.
Thank you. Hello. Hello.
Hello. Yes.
Hello. Thank you very much, Dr. Plinio. It was a very interesting session. Yeah, we may have some questions from the audience. It's time for questions. Video on, please. Yeah, we have one question here from Dr. Vimala Devi. Yeah.
Mm-hmm.
So very good day, sir. I have one question. So there have been interaction of the robot with that of the environment, handling, and so
And there is some echo. I'm not.
yeah, I think it's better here.
Yes.
So yeah, very good. So in the presentation, we have seen the robot interacting with the objects in the environment, and the robot also taking the commands through gesture. So is this these kind of interactions, the multiple combination of these interactions have been tried in the robot?
So in the grasping part, what we have done at the beginning was it was assuming that there was a programmer that was basically writing what is the sentence that you want to execute. So it was just purely text, so similar to what you do now with ChatGPT or something like that. And in the case of the social robot, in that case was was basically autonomous. So the robot was detecting the faces and the persons, and then according to that was acting. So in the social part, there was no any order actually at the beginning. The robot has a task that it has to perform. I don't know if that was clear.
Yes. And another question, is the interaction of the among the robots like an initiation of a swarm of robots kind of thing. So what could be the work or the difference in that, or whether that has been experimented or something?
Actually, we have not worked with the multiple robots at the same time. So yeah, so in that part, so there are some other labs here that work on that. So try to communicate the minimum amount of information between them, exchange the minimum information to decide what to do. But in this case, it's just one robot.
Okay. Thank you, Professor.
Any other question? Yeah. You have one more question, please.
Yeah.
Hello,
Hello.
I'm Saad, and I'd just like to know, like, how do you determine, in the case of the grasping robot, how do you determine the manner in which the robot should grasp for example, glass or cup? How do you determine that?
So in that case, what we have two types of information. So we have the high level information and the low level information. Assuming that you are able to detect the parts of the object, so then you can associate a particular behavior for each part. So for instance, for pouring object and serving, you want to grasp it from the handle, and that is actually defined by somebody. So actually somebody define those rules, and then according to those rules, then you
Okay,
basically select which part is the right one for that. You either can do that by hand, or you can infer it from looking at videos. That's what is currently persons are doing. So people are actually doing. They have, I don't know if you know this about this huge data set of basically tons of people that have cameras in their heads, and then they record them cooking. And then after you analyze those videos, you can also infer which parts of the object you should grasp. So you can do it in both ways. At the end, you have to label some parts of the data that you have.
once you have determined how you should hold it, there should also be a manner of lifting the objects, right? So, uh, for example, if you have a pan like the one you had in your video, right, and you lift the pan by its handle, then you would be tilting it, right? So, how do you determine all those things? Like, how the pan is
Yeah.
filled with
So
some, if the pan is filled with some liquid, it's going to fall over, right?
yeah. So yeah, you are totally right. So that's also we are trying to explore those things also now. So because the missing part here, the main missing part here is the tactile sensing. Actually, you need to know how much force actually you are actually executing and actually measuring both things to decide if you have to close harder or not. So that's and we are also
Okay.
exploring that. So yeah. So in this case, in the first video that I showed, it was just closing like a predefined force. So if the object was too heavy, it was not able to grasp it. Yeah.
All right. Thank you very much.
You're welcome.
Okay, thank you very much, Dr. Plinio. So with this, the first part is over. Now we have a break time.